Medical imaging and oncology rely on the behavior of billions of individual photons. Each path a photon takes determines the difference between diagnostic clarity and a useless clouded scan. In radiation oncology, these trajectories dictate whether energy is deposited within a malignant tumor or leaked into healthy surrounding tissue. Compton scattering is the primary physical interaction driving these results within human tissue. To model this interaction precisely, we must synchronize relativistic kinematics, which defines the allowed energy states, with quantum-electrodynamics, which provides the mathematical probability of each outcome. The massive scanners and linear accelerators of a modern hospital operate based on these specific subatomic probabilities. This interaction begins when an incident X-ray or gamma-ray photon strikes a target electron. The event leaves behind a lower energy scattered photon and a recoiling electron ejected from its original position. This interaction functions as an energy-momentum redistribution. As the incident photon loses energy, that exact amount is transferred to the recoil electron as kinetic energy, denoted here as T sub E. Calculating exactly how that energy is divided is the requirement for determining both radiation dose and imaging detector response. We start with the photon's energy, h nu, and momentum, E over c. The electron has a rest energy of 511 keV. At this critical scale, the scattering interaction changes. Finally, we define the differential cross-section, d sigma over d omega. This value provides the probability per unit solid angle that a photon scatters into a specific direction. Mapping the collision accurately requires all three components: photon properties, electron rest mass, and interaction cross-sections. Relativistic conservation of energy and momentum establishes the strict limits of the interaction. The incident momentum must split vectorially between the scattered photon and the recoil electron. Combining the momentum geometry with relativistic electron energy produces the Compton energy shift formula. This formula proves that the final energy of the scattered photon, E', depends entirely on the incident energy and the specific scattering angle, theta. While kinematics defines which final energy states are allowed at a given angle, it cannot predict which specific direction the photon will take. Predicting the trajectory of a photon requires shifting from a classical collision model to a probabilistic quantum outcome. Calculating the probability of each scattering angle requires a framework beyond kinematics. Quantum-Electrodynamics, or QED, provides the necessary calculations for these transition probabilities. QED evaluates the time-ordered amplitudes for the electron absorbing and emitting the photon. Squaring this total scattering amplitude yields the Klein-Nishina differential cross-section. The Klein-Nishina formula drives medical physics. Factor 1, in red, sets the interaction size scale via the classical electron radius. Factor 2, in blue, accounts for reduced scattered photon energy. Factor 3, in yellow, incorporates the quantum mechanical amplitude structure. At diagnostic energies below 511 keV, the formula reduces to the classical Thomson form, producing a broad, symmetric probability distribution. But at therapy energies around 1 MeV, the equation suppresses large angle backscatter, forcing a highly concentrated forward-peaked distribution. This shift from low-energy symmetric scatter to high-energy forward scatter is the governing dynamic of modern clinical radiology and oncology. Diagnostic CT systems generally operate at X-ray energies around 100 keV. Because this is significantly lower than the electron rest energy, photons possess a high probability of wide-angle scattering within the patient's body. These scattered photons arrive at the detector from incorrect angles, violating the straight-line paths assumed during reconstruction and causing image fog. Modern CT software uses the Klein-Nishina cross-sections to mathematically model and correct for this scatter, preserving the quantitative accuracy of the scan. A clear diagnostic CT image relies on this mathematical filtration of quantum probabilities. Radiation oncology utilizes mega-voltage beams, reaching energies of approximately 1 MeV. At these levels, the Klein-Nishina formula dictates that forward scattering dominates and large-angle events are suppressed. This forward trajectory facilitates a massive transfer of kinetic energy to the recoil electron. The destructive power of the treatment comes from the ionizations created by these fast, forward-traveling recoil electrons, which fracture the DNA within a tumor. Precise dose deposition in therapy is a direct result of this high-energy, forward-peaked quantum interaction. Compton scattering is a quantum energy momentum redistribution process. Kinematics defines the allowed energies of the collision, while the Klein-Nishina formula calculates the quantum probabilities of each scattering direction. The 511 keV threshold is the point where this quantum behavior begins to dictate clinical outcomes. The advanced macroscopic tools used in radiology and oncology are essentially engines powered by the rules of quantum electrodynamics.